Hello everyone. This topic is regarding the chapter organisms and population, which are coming under the broad category of ecology, and why we need to study the different attributes or characteristics of the population with respect to the environment will be discussed in this particular section of the video. So before starting this concept, let's see what is the exact meaning and definition for the term population. So basically, population is the term which refers to the total number of individuals of the same species which occupies a particular geographical area at a given time. And this definition was proposed by Clark in the year 1954. So most of the population, whether it could be either recognized as a monospecific population or a mixed type of population or polyspecific population, where more than different types of individual which are related to different species they are residing. So in that connection, population ecology, it's basically a term is which is being introduced so as to uh, discuss about the study of the individuals of the same species which occupy a particular space, where the processes like aggregation, interdependence between the individual, etc., and the various factors which govern such processes are being taken into the consideration. So most of the population attributes, they are summarized describing the characteristics of the population, and the population ecology is the branch which I have already told you right now, which deals with the study of the individuals of the species occupying a particular space, where processes like aggregation, interdependence between the individuals is being taken in concern or in connection with the environment. So formally, an attribute is a function that is applied to the entire population, and it determined through the variate values on the individual units. So actually we are taking the variation in numbers. It could be the size of the population, the density of the population, and we have different methods for the estimation of population density. We can use either total count method, relative density method, indirect estimation, biomass estimation, percentage cover. So these are some of the methods to calculate the population density. The attributes of interest is basically the average speed of light across the all units in the target of the population. So the development of population ecology owes much to the demography and actuarial life tables. So population ecology is important in conservation of biology, especially in the development of population viability analysis, which makes it possible to predict the long-term probability of a species persisting in a given habitat, and which is basically in the form of a patch. So although population ecology is a subfield of biology, it provides interesting problems for mathematicians and statisticians who work in the population dynamics. So the most fundamental law of population ecology is the Thomas Malthus exponential law of population growth, which is given in your book. So the population will grow or decline exponentially as long as the environment experienced by all the individuals in the population, it remains constant. And this principle in population ecology provides the basis for formulating and predictive theories and tests, which are in the form of a picture which is being shown here. You can see the population density, which is implicated and depicted through the capital N, and what are the different components which add numbers to the population density. So it could be the natality rate or the birth rate of the individuals, that is depicted by the capital B. You can see the positive sign over the arrows which add the population or numbers or individuals into the population density, that is N. Likewise, whenever there is immigration also, that is the movement of a particular group of individuals or population from one place to another place, that is also coming under the increasing the density of the population of a particular or confined area. So that is also a positive You can say this is depicted by the positive sign over the arrowheads. Now you can see the how population density it is being declining, or it can be you can say the negative effect by the mortality rate, that is depicted by the capital D. And then emigration, that is movement of the population from the particular or confined area, through which the population density estimate is being taken into the consideration. So these are all the pictorial representation for the population ecology. Now the simplified population models, which usually start with the 4 key variables, which you can see here on the picture, that is the 4 demographic processes. They include actually the death, birth, immigration and emigration. So let's see what are the mathematical models used to calculate the changes in the population demographics and evolution, which hold the assumption, that is null hypothesis of no external influence. So if there is no external influence, then how the population densities goes on changing with respect to the different you can see the factors, the 4 factors which is being mentioned here. So models can be more mathematically complex, where several competing hypotheses are simultaneously being confronted with the data. For example, in a closed system where immigration and emigration does not take place, the rate of change in the number of individuals in a population can be described as NT plus, that is total population, plus 1 is equal to N with the you can see here the birth rate plus emigration minus death or mortality plus immigration. So this is how the formula is being calculated, and the population density graphics, it is being shown in your book. So the formula which is given in your book, I have shown it in the form of this picture, you can see here, and the same formula is being written over here. Now where N is the total number of individuals in the population, B is the raw number of births, D is the raw number of deaths, and B and D are the per capita rates of birth and death respectively. So R is the per capita average number of the surviving offspring in each individual, and this formula is being read as the rate of change in the population, which is equal to the birth minus deaths. So using these techniques, Malthus population principle of growth was later transformed into a mathematical model which is known as logistic equation. And you can see what is that logistic equation, which is the exponential growth equation represented by NT is equal to N naught ERT, where NT is the population density after time t, N naught is the population density at time 0, R is the intrinsic rate of natural increase, and E is the base of natural logarithms. So this is also represented by dn dt by Rn, where N is the biomass density, A is the maximum per capita rate of change, K is the carrying capacity of the population. So these are the formulas through which the population ecology expands into a field of investigation that queries the demographies of the real population and test these results against the statistical models. So the field of population ecology often uses data on a life history and matrix algebra to develop the matrices, and this information is actually used for managing the wildlife stocks and getting the harvest quotas with respect to the conservation of biodiversity. So environmental scientists, they use 2 models to describe how population grow over time, and these models, they are given in your book. The first one is exponential growth model, and the second one is logistic growth model. So therefore a limiting resource functions to limit population growth. Let's see the first one, that is the exponential growth model. You can see here the 2 dimensions or variants which is being shown here over the x and y axis. Over the y axis we have taken the population density, and x over the time axis. A growth curve is basically a graphical representation of how a particular quantity it increases over time. So growth curves are used in statistics to determine the type of growth pattern of the quantity, be it linear, exponential or cubic. An example of a growth curve is country's population over time. So population density you can see here with time, that is dn by dt is equal to rn, where resources are limited, population exhibit logistic growth. In logistic growth, population expansion decreases as resources become scarce. Leveling off when the carrying capacity of the environment is reached, the result it will result in an S-shaped curve. So the Verhulst-Pearl logistic growth curve, and the equation for that is dn by dt is equal to rn by k minus n divided by n is the formula. You can see the logistic curve of which the formula is being mentioned over there, and you can see the population reference with respect to the time. Now, in exponential population growth, when resources are unlimited, a population can experience exponential growth where its size increases at a greater and greater rate. Formula for J-shaped curve may be summarized mathematically as dn by dt, where Rn with a definite limit on n, where n is the number of individuals on the population, t is the time, and r is a constant representing the intrinsic rate of increase. So biotic potential of the organism which is being conserved. So this was all about the population attributes which is given in your book.